Okay, review number 11. This is our most recent chapter. Should be what's most fresh in our minds. Also a huge part of the AP test. It's the highest percentage of the AP test that you have. It is about 15% of what you're going to see. One of the 6 free response questions is going to be on this chapter. So certainly something that we want to have a good handle on. What we get into in number 1 here is just making sure we understand all these tests and everything, and that when we did all those tests, the first thing that we always considered is, did it pass the nth term test? So when we look at this as a series, we have to pass the nth term test. And in this case, we would say no, because as our n would go to infinity, this would have a limit of 1. If you had to justify that, it's because of the nth term test. The limit of our a sub n terms as n goes to infinity is a 1 and not the 0 that it's supposed to be. That's for a series. So as soon as we see this here, we understand then that we are talking about a series. We are adding up all the terms. The only way a series could converge if we're adding everything up is if the limit of the sequence of numbers within it, the general term, was going to a 0. When we go to number 2, what we actually started with in that chapter is sequences. So it says if the general term in number 1 were to be considered as a simple sequence, so we didn't have the sum in front of it, would the sequence converge? Then we would say, yeah, that the limit as n went to infinity for that general term was a 1. But as a series, it's a problem because you're going to be adding that over and over and over again. All right, so that's kind of how that chapter started out, with differentiating between a sequence and a series. We then got into the next section, finding the sum of a series if it was geometric. So geometric is when we have a base that's a constant raised to a variable, very much like this one. We can find the sum of a geometric series with this idea, the first term divided by 1 minus your ratio. So our first term in this case, since we're starting in an n value of 0, if I let the n be a 0, this would all get raised to the 0 power, so my first term would end up being a 1. My ratio then, since it's 3/5 to the nth power, means I'm just multiplying by 3/5 over and over and over again. So the 3/5 is our common ratio. So that sum ends up giving us the 1 over 2/5 for an answer of 5/2. That was kind of the second section in this chapter. Then we get into all of these tests here, and we've spent a ton of time on these. Even if we were meeting this evening, I wouldn't be spending a lot of time going over all of these, just because we've dealt with these a lot. So we'll maybe do 2 or 3 of them, and then a lot of these I'll leave you. I can kind of tell you what they are, but we'll go through, hit on some highlights here. The first one is important, just understanding the alternating idea. And then that then leads us to converging absolutely or conditionally when we start having alternating series. So when you first observe this, when you see that this is alternating, the only thing that has to happen for an alternating series to converge, to be able to simply write converge or diverge, is the non-alternating part has to go to 0. So as we do the nth term test, this has to go to a 0. So if we thought that through, as n goes to infinity, I would ask, does n, as n goes to infinity, does this go to a 0? And hopefully we would recognize that, yes, it does. The function on the bottom gets larger and larger. The numerator is always going to be a 1. Passes the nth term test. It's alternating. This means that it converges. But then what we had to identify with this one, if I ask you conditionally or absolutely, is, does that converge conditionally or absolutely? The only way that would converge absolutely is if it wasn't alternating. So if I got rid of this part, would that 1 over root n converge on its own? And that should be a question or an answer of no, because this is a p-series with a p equal to 1/2, which is less than a 1. So because the answer to that question is no, then this converge conditionally. All right, the condition is that if it's alternating, it's okay, but if it wasn't alternating, it wouldn't be okay. Okay? A lot of okays there. Number 6 I want to do, just so we kind of review the factorial idea. because typically the factorial is going to require you to do the ratio test, which is all the n plus 1 factorials and when do we stop, so that we can cancel them out, get us something small. So let's go through that. All right, so on the left side, that first fraction is your n plus 1 series. So instead of n factorial, it's an n plus 1 factorial. In your denominator, you would have done n plus a 1 first. You would have distributed the 2 to get a 2n plus 2. Add the extra 1, gives you your 2n plus a 3. We don't need absolute values here. I know eventually on this packet too, we'll do the interval of convergence. When we did the interval of convergence, that's when we use those absolute values. We don't need absolute values for the simple ratio test. So as we now go ahead and simplify this, the n plus 1 factorial, I'm just going to do n plus a 1. I'm going to stop at n and put a factorial behind it, because if I look at this other denominator here, I have an n factorial that I'm going to be able to cancel. So then those will cancel. The 2n plus 3 factorial, see, I left enough room. 2n plus 3, 2n plus 2, oh boy, 2n plus a 1 factorial. I'm going to stop there. One, because I ran out of room, but also because I have a 2n plus 1 factorial in the numerator of the other fraction, so that this cancels out this. Next, I'm going to take this 2n plus 2. I'm going to factor out a 2 from that. So write that as a 2n plus a 1. So then let's say this is gone, because now this 2n plus 1 will cancel out that n plus a 1. So then what I'm ultimately left with in the numerator is just a 1. In the denominator, I have this 2 and 2n plus 3, a 4n plus a 6. Ratio test, then we find the limit as n goes to infinity. That's a 0. That's less than 1. By the ratio test, that means we are converging. And then that's what we put. Ratio test, p equal to 0, less than 1. All right. So that's all those tests. We did a ton of those. It's probably what we do the most in that whole chapter, because even when we did the interval of convergence things, all these things were revisited. We took a quiz on this. So I'm not going to spend a ton of time on these. I can tell you number 5, it converges conditionally. You would want to use the comparison test, and it would be greater than the harmonic. Number 7 is going to diverge immediately. And that is because it fails the nth term test. The limit as n went to infinity would not exist. Number 8 diverges. The faster growing function is on top, so it also fails the nth term test. The limit as n goes to infinity would have been infinity. Number 9 diverges, also failing the nth term test. That limit would not exist. And then number 10, that converges because it's alternating. This does go to 0, the sequence does. However, it converges conditionally because this is greater than the harmonic series. So that's all of those. Again, we got plenty of those. I would like to do a convergence, radius of convergence, and interval of convergence. I can tell you right now, I did not leave enough room for this one. So if you could kind of go through that. This is now the absolute value. So now we are going to do the ratio test again, but using those absolute values. So here's our n plus 1 series. And then divide by the original, which is multiplying by the reciprocal of it. The x plus 2 to the nth power cancels out this x plus 2 to the n. So the numerators would be left with an x plus a 2 to the first power multiplied by the n. The denominator, root n, sorry. And then the denominator, we would be left with a root n plus a 1. Find your limit as n goes to infinity. You have root n's in the numerator and your denominator, so those both have powers of 1/2. Therefore, the coefficients of those two terms end up being your limit. So that's really just an x plus a2. We know using the ratio test that as long as we stay underneath the value of 1, that we're going to converge. That's where our inequality comes from. So now x plus 2 needs to be less than 1 and at the same time greater than a negative 1. We could identify our radius of convergence right now if we wanted. We were centered at negative 2. Oops. If we look here, x plus 2. And if we're centered or starting at negative 2 and then we go right to a negative 1, left to a negative 3, we've gone 1 unit in each direction. So our radius of convergence would be a 1 if that was what we're looking for. That's one of the things we're looking for, but I also wanted the interval of convergence. So what that now requires us to do is to do a little more investigation of your endpoints. So since I have room, I'll do it up here. So let's test up here. I'll do the negative 3. So you're just taking this negative 3, plugging it in, seeing what series results. So if this is a negative 3, I get a negative 3 plus a 2, so a negative 1 to the nth power times 1 over root n. We may have done this one on the previous page. Alternating series, as long as this goes to 0, which it does, this should converge. So this converges conditionally. And in all honesty, if we're again just looking for the interval of convergence, we could just say that this converges. In fact, let's do it because it'll save us a little bit of time. And this is the alternating series theorem. All we're really looking for is, do I want to close the negative 3 or not? I do. And the alternating series theorem is enough proof for us to be able to close that off. We don't have to get into conditional and absolute when we're doing the interval of convergence. Go ahead, test your negative 1. Let me create some space somewhere. Try to do it right here. So if I take my negative 1 and plug it in, the series that I'm going to create is a 1 to the nth power times 1 over root n. And then we should know that 1 to the nth power is really just a 1. So that simplifies to be just a 1 over root n. That definitely diverges. And then we would need to justify that with a p-series explanation. Our p is 1/2, which is less than a 1. So the negative 1 stays open. This here is your interval of convergence. Negative 3 got closed, negative 1 did not. Number 12, writing a third-degree Taylor polynomial. This is just kind of refreshing a memory a little bit. These are typically a little bit harder. It's just knowing what our formula is going to be for this. I know it's a little typo here too. This right here should be f triple primed of 2. So if you remember, third degree Taylor polynomial for f, you're doing one of two things. If you use the f, it's an approximation. What I would suggest you do instead is write this as p sub 3 of x. It's a polynomial of third degree. And then just remember our little pattern for Taylor polynomials. The functional value goes first. And then that technically has, even though we don't need to write it, and I'm going to erase it here in a moment, we're centered at 2, so that would be to the 0 power over a 0 factorial. So those are all of our 0 derivatives, 0 power, 0 factorials, which ultimately is just your function value. And then we would do plus our first derivative value, and then x minus 2 to the first power over your first factorial. Second derivative, second power, second factorial, and finally our third derivative, third power, third factorial. And then that's that. These, in particular, when I say have these memorized, one, 2, and 3. Very, very commonly known functions. E to the x, sine of x, cosine of x, seen numerous times where your ability to identify those is going to get tested on the non-calculator part. So make sure we know what those are. We did these quite a bit here in this chapter. These you're going to want to know. The fourth one, not as important. The reason I gave you that is just understanding that's a geometric series, how this is a 1. This is 1 minus our r, so that's our ratio. Know what those are. We don't want to have to prove those for the types of questions that you're going to get, like number 13. So for number 13, you would have two options here. If I ask you to find the 10th degree Maclaurin series, that doesn't make any sense. A 10th degree Maclaurin polynomial, let's do that way. The reason that doesn't make any sense is a 10th degree means we only go to the 10th power. The series means we write all the terms, which is basically the general term. So a 10th degree polynomial means we want the 10th polynomial term, so the 10th power, 10th factorial, 10th derivative. So that, just me explaining that, is why you want to have what these are up here memorized, because if we don't, you need to hammer out 10 derivatives. We need to go derivative, second derivative, until we get to the 10th derivative, and then we need to do what we would have done up here using our little pattern, the Taylor series polynomial formula, to go through all of that. That would obviously be a nightmare, versus understanding that if I know that sine of x, what do I want with this? I don't like how I have this worded. Yeah. That the sine of x is these here. Think about a 10th degree polynomial. If I did x to the first over 1 factorial, and then it alternates x cubed over 3 factorial, x to the 5th over 5 factorial. If I know that, let's use an approximation right now, then the sine of 2x squared is really just us taking this 2x squared instead of x, plugging it in here, here, and then right there. So I would get 2x squared over a 1 factorial. If I plug in a 2x squared right here, that is going to give us what? 8x to the 6th over 3 factorial. Plus, and then 2 to the 5th would be 32. Yeah, so 32 x to the 10th over a 5 factorial. And then that's it. That's our 10th degree Taylor polynomial. Again, you could... I wrote it as the equivalent, so we understand just whatever I do to one side, I do to the other. But if we want to use an equal sign now, we could go ahead and say this is P sub 10. It's our 10th degree Taylor polynomial that we are using to approximate that function. Keep in mind, if you ever have to take the derivative or integrate, as long as we have an equivalent statement. So on the left side, maybe the function. On the right-hand side is the series or polynomial that represents that function. Then whatever I do to one, I could do to the other. That is best demonstrated here. If I write cosine is equivalent to this. If I do the antiderivative of this, it should just be the antiderivative of this. Notice how if I add 1 to this power, I get an x to the 2n plus 1, and then I would divide by that, right? And you just happen to get the sign. The antiderivative of 1 is x, which is still x to the first over 1 factorial. The antiderivative of x squared would give me x cubed. Get rid of that. divided by a 3 factorial, which then gives me 3, 2, 1. So just understand, as long as we have equivalent statements, whatever I do to one side, I can do the other. We've done derivatives, we've done antiderivatives with those. All right, then some multiple choice questions on this. So 14, we've done one of these where if this is the first 4 terms of a Taylor series expansion for some function about x equals 3, then you're given those 4 terms. What is the value of the second derivative at 3? So what we would want to focus on is this here should be your function value. So this should be f of 3. And then since this is our first derivative, first power, somewhere in here we would have had our first derivative divided by our first factorial. Since I'm looking for f double primed of 3, what we're focusing in on is this one right here. Because what we should have in a Taylor polynomial is our second derivative, in this case at 3, minus x minus 3 to our second power, and then all divided by your second factorial. So again, second derivative, second power, second factorial. Well, when we look at the term that we are given right here, here's our x minus 3 squared. Here's an x minus 3 squared. What had to be true is that this combination of the second derivative divided by 2 factorial had to have equaled the negative 7 over a 3. So f double prime to 3 over 2 factorial equals a negative 7/3. Multiply that 2 over, should give you a negative 14/3, which is letter A. We've seen that a few times now. Really common question. 15. So it says, which expression below represents the first 4 terms of the Maclaurin approximation to the area underneath f of x equals e to the x squared? This is a non-calculator question, and you may be thinking, how am I supposed to do that if I don't know what this curve looks like? And that's a legit question. But what you want to focus on more than anything is that an exponential function cannot cross the x-axis. So as long as we know the general shape of an exponential curve and that it can't cross the x-axis, doesn't this have to look pretty much like this? It's going to increase a little bit quicker than the regular e to the x graph because it's an e to the x squared, but it's still going to take on that general shape. We're going only from 0 to 1, so this would be the area that we are looking for. All right. So if I ask you to set up an integral for this, all you're integrating or setting up is the integral from 0 to 1 of e to the x squared. That is not something you could do by hand. Like, we don't know the antiderivative of that. None of our integration methods are going to work. So the way we're going to do that is we're going to do it using an approximation method, and that approximation method is our Maclaurin and Taylor polynomials. So the way we would want to understand or approach this is with the understanding that e to the x, if I want the first 4 terms, would be 1 plus x to the first over 1 factorial, x squared over 2 factorial, x cubed over 3 factorial. Those are our first 4 terms for e to the x. All right, well, what we want is e to the x squared. So all I'm doing is changing my composite. So what I'm going to do on the other side is the exact same thing. Instead of x to the first, I'm going to have x squared to the first over 1 factorial. Up here, instead of x squared, I'm going to do x squared squared over 2 factorial. And then the final one here, the 4th term, instead of x cubed, I need to change that to be x squared cubed over 3 factorial. All right. Well, this has now created the function that I want. All right. So if I want to integrate this from 0 to 1, then I would want to integrate this from 0 to 1. So that's what we're going to do. Now, I'm going to have to go into this next question, so I'll erase it. Hopefully you're writing smaller than I am. So let's go ahead and do this right-hand side. So the antiderivative, actually, let's simplify this real quick. We're going to want to have these simplified before we do our antiderivative. 1 is good to go. This is really an x squared. This is x to the 4th over 2. And this is x to the 8th, 3 factorials, 3 times 2 times 1, which is a 6. So we're really just doing this guy. I don't know why I put an 8 there. I said 6 and then wrote 8. All right, so let's do this. X. So now we're just doing the actual antiderivative. X cubed over a 3. X to the 5th, divide by 5 with the 2 already down there is a 10th. X to the 7th, divide by 7 with a 6 down there is a 42. We're evaluating this over the interval of 0 to 1. If you plug in your 1, that's pretty easy. Plug in your 0, that's even easier because you're going to get zeros everywhere. So what we end up with is letter A. All right, not easy. And you really can only handle that if we understand how to take e to the x as a series and know that. All right, so we have to know that e to the x is this 1, and then x to the 1 factorial, x squared over 2 factorial, x cubed over 3 factorial. That can't get done without us knowing that. Okay? Same with 16. We have to know that sign. So hopefully we have this. If not, pause me because I'm going to start to erase it all. So when we look at this, it says let f of x be x times sine of x. So get rid of all of this. To me, this is, again, another hard one. If you wanted to pause me, see if you can get through a hard one, this absolutely is a hard one. So f of x equals x times sine of x. And I want you to list the first 4 non-zero terms for the Taylor approximation for f primed about x equals 0. So what we would want to know is that sine of x is the x to the 1 factorial minus x cubed over the 3 factorial. So let me get a few of these written down. We'll go to the 4th one since I want the first 4 non-zero terms. So that's sine of x. Well, what we want is x times sine of x. So if I want that, all I got to do is multiply sine of x by x. What that then means over here is I'm going to multiply this by an x. Okay, let me use an approximation here as well. So x times sine of x, this is an approximation because we don't have them all, we're just doing the first 4 terms, is if I go ahead and now multiply all of these out, x squared over 1 factorial, x to the 4th over 3 factorial, x to the 6th over 5 factorial, and then x to the 8th over 7 factorial. So we have now created this first little sentence here. We've created the function f of x, at least an approximation for it. What the question is now asking you to do is find f primed. So if this is f of x, it's our approximation for this function. If I now want the derivative of this, couldn't we just take, instead of doing product rule and all this, the derivative of this guy? So the derivative of x squared is just a 2x. Then I would get 4x cubed over 3 factorial plus 6x to the 5th over 5 factorial minus 8x to the 7th over 7 factorial. That's what we're looking for. The first four non-zero terms for f primed of x. So if we now look at that and start looking for that answer, we should see that that matches up to letter B. (17) What are all values of x for which this series converges? This is just an interval of convergence test. We've done a ton of these. It's probably, again, one of the couple of things we've done the most of with this chapter. So I'm going to leave you this. It should be, which one? This one. So if you wanted to go through, make sure you can do an interval of convergence. It's just k's instead of n's. Sometimes they'll throw a k out there. If you just let the k's be an n, it's the same exact thing that we've been doing over and over again with the interval of convergence test, but that should be a d. I'll leave you that one if you want to try it on your own. And then 18, another one that you really need to know what that exponential series looks like in order to be able to get through this one. So I'm giving you f of x is e to the 2x squared. Find the first three terms for its derivative. Find the first three terms of the Maclaurin series for the derivative of this. So again, we want to know e to the x. We want to know what the polynomial terms are in that series. All right, so we get that. We can continue on if you want. I want you to create e to the 2x squared. So that just means we're going to come over here. Wherever we have an x, we're plugging in 2x squared. All right. Wait a minute. Get that down. We then want to ultimately, now that we have created this function, we want to take the derivative of that. Before doing so, probably a good idea to just simplify this a little bit. And then now take your derivative. So if this is our approximation for x right now, or for f, this should be approximations too, then the derivative of that, sorry about that, one would go away. I'm going to get a 4x right away. Probably tells us that our answer is D. It's the only one that starts with the 4x. First, hold on a minute. Hold on. Yeah. And then plus, this is x to the 4th here. Yeah, so 16 x cubed over 2. All right, yeah, definitely D. And then 48 x to the 5th over 6. Yeah, which is 8. Yeah, so definitely D. Sorry. The dogs and cats fighting in here distracted me for a moment. Thought I messed that up. All right, so that's that one. All right, then we get into all these free response questions. We've done a bunch of these already. Guarantee you're going to get one of these. So you want to be able to handle these reasonably well. So for number 6, and it's almost like this is number 6. I think the next one is number 5. It's typically one of the last 2 questions on the free response portion. So you're already pretty mentally exhausted. And then they throw these questions at you. Sometimes they're hard, sometimes they're nice, sometimes they're somewhat in between. So just cross your fingers when you get this question. Let f be a function with derivatives of all order, and then they're telling you that f of 2 is 7. If n is odd, so if n is a 1, if n is a 3, 5, your nth derivative is 0, so you're not going to have that term at all. When n is even, and n is greater than or equal to 2, your nth derivative can be found using this formula right here. Write the 6th degree Taylor polynomial for the function about x equals 2. Okay, so what we would need is our functional values, this is letter A, at 2, and that's given to us, so that's nice. We don't have to worry about our odd derivatives, right? Because the odd derivatives, if n is an odd, that's going to give you a 0. So we're going to have nothing but even powers here. We're going to have our 0 derivative and 0 power, and then our second derivative, second power, fourth power, sixth power, so on and so forth. So we need our second derivative at 2. To find that, if n is an even power, we're using this formula right here. So let your n be a 2, and we get 1 factorial over 3 squared. The third power is going to be a 0, so a third derivative is. So the fourth derivative at 2 should plug in this formula here, 3 factorial over 3 to the fourth power. We want the 6th degree, so I need one more. So I'm just going to write 6. Derivative at 2, plug in a 6, we would get 5 factorial over 3 to the 6th power. So those are our derivatives. So now if I want the 6th degree Taylor polynomial, let's put this together with our formula, so the functional value, and then I would want the second derivative, and then x minus 2 to the first power, or second power, over our second factorial, plus our fourth derivative term, so 3 factorial divided by 3 to the fourth, x minus 2 to the fourth power over 4 factorial, plus our fourth derivative, x minus 2 to the fourth power, I'm sorry, our sixth power, it's our sixth derivative, over 6 factorial. If that's all they're asking you to do, there's no reason to try to go through and clean all of that up. Okay, I'm just kind of asking for trouble a little bit with doing that. Let me make sure I'm just double checking my work, make sure there's a lot going on here. I think we're good. All right, and then letter B, in the Taylor series for f that we just found in the previous question, what is the coefficient of x minus 2 to the 2n power? So what that's asking, this is the shading, yeah. Let me change to yellow. This is x minus 2 to the 2n. This is an x minus 2 to the 2n. X minus 2 to the 2n. So if I put this little guy here, oops, and that's a sigma sign. That's really ugly. Let me try that one more time. And we start down here at the 0. We're going to have this infinite series that we just created right there. Well, if n is a 0, you're going to get this 7. If n is a 1, shouldn't we be getting 2 times 1, which is 2, which we do? And then if n is a 2, notice how we get a 4. And if n is a 3, this exponent is a 6. So the things that I have highlighted in yellow, those are the x minus 2 to the 2n terms. So if that's what I have highlighted in yellow, what letter B is asking you, how could we get their coefficient? So what's a little expression for this? What's an expression for this? So what expression, what general term for the derivative would create those three things that I just circled? So, you could try it. A couple of them are easy, right? Isn't the denominator, isn't this 2n, just like this was a 2n? This is just a 2n factorial. This would have been a 2n factorial. This is a 2n factorial. Isn't this 3 to the 2n, right? 3, 2 times 1, 3, 2 times 2, 3, 2 times 3. And then the numerator for this, a 1, a 3, a 5. If you think that through a little bit, that would have to be a 2n minus a 1. And then they're all factorials. So we get a little 2n minus a 1 factorial. Okay. So, not easy. Even as I look at this, the reason I'm kind of going very slowly right now, I'm just making sure I didn't screw something up. I think we're all good there. No, see, I did screw something up, because shouldn't this be 3 to the 2n? Yeah, so then we get 3 squared, 3 to the 4th, 3 to the 6th. All right, now I'm pretty certain that is good to go. All right, and then letter C, it says find the interval of convergence for that Taylor series. Again, I'm going to leave that for you. It is a bit of a nightmare because this is now your derivative. So maybe I'll get you started on this. You may even want to simplify that a little bit. So let me go ahead. This is the 2n minus a 1 factorial, 3 to the 2n, and then the 2n factorial. That's just the derivative part. And then you'd still have this x minus 2 to the 2n. That's what you're going to do the interval of convergence with. A lot going on there. A lot of n plus 1s, a lot of factorials, a lot of things to kind of clean up there. But what you should ultimately get to is that this converges everywhere. That this is going to be one of these guys that your limit as n goes to an... Oh, no, hold on. My bad. Should be what? Negative 1 to 5. Sorry, I'm looking at the wrong problem here. All right, should be from a negative 1 to 5 in terms of where that thing is going to converge. Okay? All right, last one. Says consider that differential equation. Let y equals f of x be a particular solution to that differential equation. And then they want you to find the first derivative and then the second derivative value at the negative 1, negative 4. So dy dx, letter A. First one's pretty straightforward, right? We want to figure out the value at negative 1, negative 4. So we can just plug in that. So we would get 5, negative 1 squared. Which is what? 5. So we get minus negative 1, so 5 plus 1. So that should be 6. Then we need the second derivative of this. So the second derivative of y with respect to x, it should be 10x. I'm going to guess the next one, most of us would probably do the quotient rule right here. So we'll go through with that. It's your bottom of y minus a 2. Derivative of the top is 0. And then minus the top. The derivative of the bottom is the derivative of this little y, so dy dx. And then all of that would get divided by your denominator squared. Let's clean this up a little. So this would become minus, this would have canceled, negative 6 over y minus 2 squared. This is our dy dx. And then we ultimately ended up adding those. Now we evaluate this at the point, negative 1, negative 4. So this is 10 times a negative 1 plus 6. And then you could substitute in your dy dx, but don't we already know? So here's our dy dx. So we could plug that in and then evaluate it at negative 1, negative 4. But isn't that what we did earlier? Didn't we already take dy dx at the negative 1, negative 4 and get a value of 6? So couldn't we just right away say that that is going to be a 6? And then divide that by the y minus 2, with y being the negative 4. So that's a negative 2, or negative 6 squared. And then, let me make sure here. Yeah, because that will give you a negative 10. Plus, and then this works out nicely. This is the 36 in the numerator. This is the 36 in our denominator. And we should get a negative 9. B, it says, is it possible for the x-axis to be tangent to the graph of f at some point? So for letter B, understand what that's now asking. Is it possible for the x-axis to be tangent to the graph of f at some point? So instead of them asking you to write the equation of a line tangent, which has been done over and over and over again, just a little different way to test you on this idea. So there's two things that has to be true if your graph is going to have a tangent line at the x-axis. So what we always share is a slope. Remember, we always talk about our slope and then our point. So if we are tangent on the x-axis, doesn't the x-axis have a slope of 0? So one of the things that must be true for tangent on the x-axis is that your slope would have to be a slope of 0. So if we did that, take your slope, which we were given, right? This is the slope of this curve anytime we want it. And that is 5x squared minus 6 over y minus a 2. And we are basically determining, does this equal a 0? Well, at this point, we have a problem because we have two different variables. So there's one other little element that they're testing you on, and that is the idea for tangent on the y-axis. On the y-axis, doesn't your does it say it's x-axis, right? Yeah, on the x-axis. So on the x-axis, doesn't your y value have to be 0 whenever we are crossing the x-axis? So we wanted to be tangent, so they have to have the same slope on the x-axis. So on the x-axis means we know that y has a value of 0. So that's what we're going to do. Not only are we setting it equal to a slope of 0, what I'm also going to do is allow my y to be the y coordinate of 0, since we're going to be on the x-axis. So what we end up with then is, let me save some room here, is the 0 is equal to 5x squared. You get negative 6 divided by negative 2 plus a 3, we subtract that 3 over, and then we start to see we're going to have a problem, because eventually we get to the square root of a negative 3/5. So it's not possible. Let me see what they asked us to do. Is it possible? And it says explain why or why not. And then we would just need to put this into words, because when y equals 0 and dy dx equals 0, the value of x is imaginary, or gives us a complex number or something along those lines. But basically just say when we let the y be a 0 and our dy dx equals 0, we get an x value. That's some sort of a problem. Then, why do I give you this in this Taylor series, polynomial, all that stuff? It's because they then randomly throw this out into this problem. So it now says, because again, up through A and B, there's nothing to do with a Taylor series, Maclaurin series, interval of convergence, anything. But then you get to part C, and it's now asking you find the second degree Taylor polynomial for your function about x equals 1. So second degree Taylor polynomial, we're going to do it about the x value of the negative 1. So second degree means we need p sub 2 of x. And then we want our functional value at negative 1. We want our first derivative value at the negative 1 with x plus 1 to the power of 1 over 1 factorial. We want our second derivative at a negative 1, x plus 1 to the second power, 2 factorial. Now, the nice thing about this is you've already done this work, right? Like f of negative 1, we know because it's this point, when x is a negative 1, we have a y value of negative 4. Then I need my first derivative value at a negative 1. Isn't that what we did in part A? Right? We found our derivative value at the x coordinate of negative 1, and the first derivative value was the 6. And the second derivative value at negative 1, we also found, right? So here's our second derivative at the x value of a negative 1. We found that to be a 9, or negative 9. So we do negative 9, x plus 1 squared, 2 factorial, and then that's our second degree Taylor polynomial. That's why I like them, the way they write their tests. They're very creative, and you really have to know everything because they find ways to just test you on random things at any point in time. So it's good and bad anyway, just because you really need to know your stuff pretty well. And then not only that, they then lead you into an Euler's method. So throughout all of this, they're combining a bunch of different ideas into one little problem. So it says, using Euler's method, starting at the x value of a negative 1, with 2 steps of equal size, approximate f of 0, and then show the work that leads to your answers. So, man, I don't have any space here. I am going to erase a little bit. I want to keep part A because that's going to help us, if I remember correctly. Thinking this through correctly. All right. So Euler's method. If we're looking for Euler's method, if you remember, if I want my, let's first talk about, we know f of negative 1 is a negative 4. The question is asking you to find f of 0 as an approximation with 2 steps. So if I need to go from a negative 1 to 0 with 2 equal steps, that means I need to be going by a step size of 1/2. So then our change in x, we always want a step size. Oh my goodness. It has to be a 1/2. Hold on a minute. All right. Sorry for the freak show around here this morning. Not sure what's going on. Such is my life right now. So let's finish this. So where were we at? Negative 1, 4. We're looking for 0. And we're going to go from a -1 to 0 with 2 step sizes, so we know that our step size is going to be a 1/2 each time. So Euler's method. We need 2 of these. Our first one, what we did is we took the initial y value plus our initial derivative value, and then we multiply that by our step size. So that's kind of the general formula for general route whenever we're doing a Euler's method problem. So our first approximation, y sub 1, should be our initial y value, which is this -4, plus our first derivative at this point. And again, we know this, correct? We found this at the beginning of the problem. That is the value of 6 right here. So that's going to be your 6. And then our step size we know is a 1/2. So the first approximation is a -4 plus 3 for a value of a -1. Then off to the side here, and I didn't leave enough room, so bad planning on my part, I'll do it right here. Know what point you are now at. We are now at the point x is a -1/2, and when x was a -1/2, we got a y value along that of a -1. To find our second approximation, then, we now need that previous y value, which is the -1, plus our derivative at that point multiplied by our step size, which is the 1/2. So we now need to calculate this derivative at this time right here. So this is where it gets a little ugly, because we now need to, here's our derivative, right? This is how we're going to calculate our derivative. We don't know what our derivative is yet at this new point. So we're going to take that 5x squared. Let's see if I can keep both of these in there. So the 5x squared, let x be the, what is it, -1/2. Yikes. So let me do this over here. So 5 times the -1/2 squared minus 6 over the y minus a 2. And then we now know our y is a -1 minus a 2. So this should give us what? 5/4. And this would be a -6 over -3 plus 2. So what is that? 5/4 and 8/4 is 13/4. So that's our value. And honestly, at this point, other than, so I would leave this as your numerical answer. They will take that as your answer. The one thing we do want to change, though, before we determine that this is our answer, we don't want to leave this as y sub 2. We don't want to leave this as an equal sign. We now want to state what they were looking for. What they were asking us to find is to approximate this f of 0. So that's what we want to present our answer as, that f of 0 is approximately whatever this is. You wouldn't have had a calculator in your hand for this. Certainly something we should be able to do, but not necessarily something that you want to do right now when you don't have a calculator, and it doesn't matter whether you simplify it or not. So we did 4 or 5 AP questions in class on this, Taylor series, Maclaurin series. We just did a couple more. Yeah, you can't get enough practice on it. The more you see, hopefully the easier it is for you to understand sort of the shortcuts and things that they're looking for you to do. All right, so with that, we'll see you guys later.